Good afternoon, everyone. My name is Olasoji Dunloye. I am a software engineer at Intel. This is my first time at the summit. It's good to be here. I work in the open source databases team at Intel. We've worked on persistent memory for the last 2 years. We've developed libraries for persistent memory in Java. Today we'll look at applying persistent memory to open source frameworks like RocksDB, Cassandra, Redis, Memcache D. And so today is just going to be sharing some of the things that we've learned, some things to do, what not to do, and how you can apply persistent memory to modern software architectures. So the agenda, I'm going to spend some time talking about persistent memory itself, what it is, how you use it, and then we'll jump right into the use cases, examples of how persistent memory can be used and is being used today. If you have any questions, you could ask. You feel free to interrupt, or you could just wait till the end. So persistent memory, what is persistent memory? Persistent memory, it's a new memory technology that has attributes of both memory and storage. It's fast like DRAM, and it's persistent like storage. Looking at the storage hierarchy diagram here, you can see DRAM at the top, fast, smaller capacity, and spinning drives, HDD/tape at the bottom, usually used for cold storage because it's slower and has a large capacity. So persistent memory would slide in, sorry, let me get the pointer. Yeah, slides in right about here in this diagram. Again, it has more capacity than DRAM, not as fast, and it's faster than your fastest SSDs today, but slightly smaller capacity. So some of the properties of persistent memory, it is memory. It's byte addressable like DRAM, unlike files where you have to access data block by block. You can also have direct user level access. In some modes, you don't need to go through the kernel page cache or any kind of drivers. It also lowers DRAM footprint. If you are offloading some of your data structures from DRAM to persistent memory, then you're using less DRAM, and you can save money on your deployment. It also works with both file and memory APIs. I'll talk more about that soon. Now, the Intel Optane memory has multiple modes. There's the memory mode and the app direct mode. In memory mode, your persistent memory acts as your main memory. So your DRAM is essentially a cache for your main memory. The operating system doesn't know the difference and doesn't even see the DRAM. It just sees your persistent memory as your main memory. You typically use that without any code changes. You can just run your applications like you would normally using persistent memory, and it's all good. And then this is also a volatile use case. So once your system reboots, all the memory is reinitialized. In app direct mode, which is most of the use cases today are going to be based on, the OS is aware of persistent memory. And I'll show you in the next slide how you could get at it. So this is the CINVM programming model, or the persistent memory programming model. SNIA is the Storage Networking Industry Association. They're here at the conference. So they published this model, and essentially this is how you use persistent memory. So currently today, I mean, some of you are probably familiar with this stack right here. Essentially, you can use persistent memory as you can use SSDs today. So if this is your application, you can use it as a raw device going through the driver, or you could put a file system on it and then write files to it like you. Or you can put a file system on it, and you can write to it like you normally would an SSD. If you had a persistent memory aware file system, persistent memory aware file system is one that has DAX support. DAX is direct access. What that means is it does not participate in the OS page cache, right? So you can also use it in that way. You could again, put a persistent memory aware file system on your namespace, and your application can write files as it would normally. Now, another mode that you can use it as, and this is really the heart of the persistent memory programming model, is you can memory map a file on this persistent memory aware file system. And what happens is you get a pointer to, in your process address space directly to the hardware. So this is the byte addressable mode, and this, you don't have to go through the kernel, meaning no page cache, no driver. You can do loads and stores and whatever you want from there. So just to reiterate, for the app direct mode, there are two ways that you can use it. You can use it just as you would an SSD. We call that storage over app direct, right? So, excuse me, the same way you would direct your application to a mounted file system to tell it to go ahead and write files. You can do the same thing with persistent memory, no code change or very minimal code change. And the other route, you could go the byte addressable route, where you memory map a file. All right, so over the years in our work with persistent memory, we've identified some use cases. This is definitely not all of them, but these are cases where you might want to, if you wanted to apply persistent memory to your application, you might start with things like these: caches, stores, and buffers. I don't have to explain this to anyone, but caches are data structures for fast lookup. Those are good candidates to move from. They'll typically reside in DRAM for the speed. It's a good candidate to move to persistent memory. Your stores, where you persist your data, typically on disk. Also another good candidate to move to persistent memory. And then your buffers. A buffer is essentially, what I mean by buffer is temporary store. Where you write data temporarily, and then you flush it to see your persistent store later on. So all of these are essentially areas where you might want to move from the existing, whether disk or DRAM, to persistent memory. Another thing I wanted to point out is there are two ways that you can use it. You can use it either as volatile memory or persistent memory. So volatile use of persistent memory or persistent use of persistent memory. I should also point out that whenever data is stored on these persistent memory devices, it's always persistent. So really, volatile use of persistent memory is really the application saying, yeah, I don't want to recover the data when the process restarts or the system restarts. But the bytes are already there, so you have to actively throw it away. So I'll start with caches for the use cases. Again, caches are fast and lightweight data structures, right? So if you plan to move a cache to persistent memory, better make sure that it remains fast and lightweight. But again, because persistent memory is memory, whatever data structure that you were using on DRAM, you can just use the same thing on persistent memory, right? Typically, caches live in DRAM for speed, and they're constrained by size. So by moving a cache from DRAM to persistent memory, one of the big benefits you're getting is now your cache can be a lot bigger, right? Because persistent memory, you have terabytes of that. So your cache can be a lot bigger, and if your cache is a lot bigger, it can mean better performance because you can now get higher hit rates on your cache. Also, if you're interested in a persistent cache, you can get faster restart times using persistent memory. Again, the memory is already there. If your system goes down, comes back up, you load the data, and your cache is hot again, as opposed to spending minutes or hours, depending on the data size, trying to rebuild your caches. So I'm going to talk about a few examples now. And the following use cases are about optimizing caches or caching for persistent memory. So HBase. I'm going to start with HBase, the HBase bucket cache. So HBase is the Hadoop database. It is a distributed NoSQL database built on the HDFS file system. We can see a diagram of the read path here. And we can see that the block cache is on the read path. And the HBase bucket cache is an instance of a block cache. So again, like I described, if you decide to move your block cache from DRAM to persistent memory, and you can get it a lot bigger. Now you get a lot more hit rates, and you improve your you improve your average read latency, right? So in HBase, the bucket cache, the cache that manages buckets of memory of fixed size blocks. You already have the option in HBase to allocate or provision memory in different ways, whether on the JVM heap, off heap, using mmap, and now you have a persistent memory option as well. So what you do is you point it to a file on a DAX, on a persistent memory aware file system, and so it uses a memory map file allocator type, like I described in the SNIA slide. So yeah, once you do that, now, by the way, all of these changes are already upstreamed in HBase trunk. I've provided a link to the Jira here. So this is already being done, and you could go experiment with it right now and see the benefits. The next example, Memcache D. Memcache D is an in-memory key value store. It's typically used as a cache, again, designed to be simple and fast. The diagram on the right describes very simply, the internal structure of what it looks like. So on a lookup, your key, you look it up in the hash table, you get a pointer to slab memory. The slab is where items are stored, so where the key and value pairs are actually stored. In Memcache D, there is now a restartable cache option. Again, this is also upstreamed. What it does is there's another custom map file, memory map file allocator. You can point it to a file. The file could be on a persistent memory aware file system using on persistent memory. It doesn't have to be, but it could be. And then what they've done now is there's a hybrid data structure where you have your hash table still in DRAM, but your item memory is now on persistent memory or this new memory mapped file pool that you provided. Now what this means is on a restart, well, in order to be able to restart it properly, on a controlled shutdown, you need to make sure you flush the caches because persistent memory is still cache coherent. So if you want all the data to still be there, you need to make sure you flush on a controlled shutdown. And that's one of the prerequisites for the Memcache D restartable cache if you want to be able to recover your data. So make sure you flush, although you don't have to do this yourself. The application takes care of that for you. And then on a restart, they also rebuild the hash table. So they walk through the slabs and rebuild the key value pairs in the slabs, and they rebuild the hash table. Again, I provided a link to the restartable cache option on Memcache D. Now, another thing, well, again, the benefits of doing this is now your cache can be a lot bigger because of the capacity that persistent memory affords you. Another option that they could have done, they could have kept the original design and just take a snapshot of the cache. They didn't do this, but I'm just trying to tell you the ways that you could use persistent memory. If you wanted a restartable cache, on an orderly shutdown, you could serialize all of your data onto a file on persistent memory, and on startup, you deserialize and read that file back and have a restartable cache. So snapshotting is another thing that you could use persistent memory for. This is another example of a cache. So there is a project called Spark OAP, which is an optimized analytics package. It's essentially an accelerator for Spark SQL. And it was built by some folks at Intel. So in it, there's an I/O cache for which they decided to use the Persistent Memory Development Kit, PMDK. And in that kit, they decided to use a library called libvmemcache. So first of all, PMDK, Persistent Memory Development Kit, is a suite of libraries that helps you with your persistent memory needs. It has low-level libraries that provide help you provision persistent memory, or it helps you allocate memory. It gives you transaction support, and there are other high-level libraries that like this cache or a key value store, and it's all open source. So I just use this as I'm mentioning this example just to tell you all the options that you can use. There are even ready-to-go caches in this open source PMDK suite. So it's an open source cache, it's a volatile LRU cache. It's also sort of hybrid. The keys are in DRAM and the values are in persistent memory. And I provided a link for you to go look it up. So now storage. Storage is the question.
So this, the session you mentioned was for cache purpose, right? So for the cache purpose, you are using the memory mode or you are using the app direct mode?
All of these examples are app direct mode. Right. Yeah. So again, memory mode is transparent to the OS. You don't know that there is persistent memory.
If you are using the memory mode, that means the DDR, the DRAM, you use it for cache purpose, and then the persistent memory is for the system memory, right?
Yes.
So then how come the previous slides, you put a slab in the persistent memory?
Okay, excuse me. So in the memory mode, the DRAM serves as a cache to your main memory. The OS doesn't know about it. So in this case, this is either HBase guys or Memcache D people knowing that, okay, I have this memory here that I can provision. I'm going to use it as a cache. Right? So this is what app direct mode is. That's why the main distinction between the two modes. And again, just to reiterate, in memory mode, it's always volatile.
Yeah, but question. Can you go to the slide 9? I want to understand that the right path you took to the mem store rather than the HBase. And you also mentioned, I think the other side is the direct memory block, memory block copy.
The bucket, excuse me, the bucket cache?
Yeah, block cache.
Mm-hmm.
So I was wondering, like, instead of the right path going here, if I write to the block cache, that anyway going to get the persistence with the other option, right? Is that possible?
Yeah, excuse me. So depending on the level of, yes, you can make the entire thing. You put the mem store on persistent memory, right? I'm just giving a real example that has been done.
Is there capability from the mem store to block cache so that I can use that as persistence?
Yeah, you absolutely could. It depends on the amount of engineering effort you want to put into this. So this is just an example of how the bucket cache was implemented with persistent memory. I think there is an effort, or at least, yeah, I think there's an ongoing effort to, or they're considering putting the mem store on persistent memory. We've done something, I'll explain it in the storage, well, I'm about to jump into it now, but we did something similar in Cassandra, where we essentially moved replaced the disk with persistent memory. I'll talk about that in a minute.
And this is by instrumenting a code with all the necessary CL flush operations to get data to, but we use block to.
In which case?
In the Cassandra case, or in any of these cases described, you actually modify the code to do the necessary persistence directives, like CL flush, SFENS, etc.
Right, so those are, and I'll talk about that, that's a good question. Depending on your data integrity needs, you might need to flush to make sure that it actually gets to the media. Or if it's a volatile cache, you don't care. If the system crashes, you're going to throw it away and rebuild it anyways. But that's why in the Memcache D example, if you wanted to restart it, if you want the data to be consistent, when you bring it back up, then you must flush.
I'm confused because you said it's app direct mode. Why would you use app direct mode if you didn't want durability? If you just want a volatile cache, memory mode is fine.
Yes, but then in memory mode, you cannot pick and choose where, the application cannot pick and choose what data goes in DRAM and what data goes to persistent memory. It's all transparent to you. But if you use app direct mode, even if you don't want the persistence, you can use it for the capacity. So now I want a bigger cache.
Oh, I see. So you actually put the cooler data, was possibly in the PMEM, and you use DRAM for hot data. Is that the intent?
Yes, that could be, yeah. Any other questions? All right. So let's talk about storage. Typically, you use storage to persist data. Again, it's typically on SSDs or large capacity spinning drives. At least I don't know if anybody still uses spinning drives. So the benefit that you would get in this case from moving your data from disk to persistent memory, the obvious one is that persistent memory is a lot faster than like the fastest NVMe drives, for example, right? And also, again, persistent memory is memory. So you could store, you could use hash tables, whatever hash tables, trees, sorted maps, whatever data structure that you use in memory, you can still use it on persistent memory. So because it is memory, there's no need for serialization or deserialization to files, right? So it saves some complexity there. Also, the update in place, because it's memory and it's fast, if your data resides on disk, you will lose performance if you update in place on disk, right? And I'll explain it when I get to the Cassandra and read-write path. So in any case, because now you have mutable data structures, there's no need to serialize or deserialize because your data structures are going to persist even after your system restarts. You can have simpler code, and I'll explain this in a minute. So Cassandra is one of the, we use this as a POC. Cassandra is a distributed NoSQL database. It's very popular. Similar to HBase, but here we're trying to put the data store on persistent memory. Right. So right now, the default Cassandra write path with disk, this is what it looks like. On a write, you write to a commit log on disk, and then you write to the mem table in memory on DRAM. And then after some time, this is after the query after this write operation has finished. Once the mem table reaches a certain threshold size, you flush to disk in the form of an SS table. Right? On an update, if you wanted to do an update, if you had already, an update is the same. You don't update in place because if your data is already on an SS table, you don't want to add more latency to that update operation. So updates look like brand new writes, right? So it's possible that you can have multiple copies of the data, one in memory or one on disk, or even both of them on disk in two different files. So you have to compact them eventually. So compaction is another bit of complexity that exists today in this design. Now the read path, slightly more complicated. There are all of these data structures, caches, and filters, and they all exist in order to improve your disk I/O. Right? The only reason to have caches or Bloom filters is really to short circuit your read to the disk, so you are not scanning and spending all of this time. So essentially, the read path, a response comes in, you query the mem table, and you query your SS tables on disk as well. You get the results, merge it, and return to the user. So at this point, we're thinking, okay, well, we have persistent memory, it's faster, we can update in place. Do we really need all of these caches and all these indexes and Bloom filters for our design? The answer is no, not really. So this is what we came up with. The write path now looks like this. The persistent memory storage engine, I'll explain the internals in a bit, but essentially what happens is you do on the write path is simply a synchronous write to a data structure that's on persistent memory. You can think about it as a concurrent map, if you will, but that's exactly, this is exactly what it looks like. There's no write-ahead log because we do transactional writes. I'll explain what that means in a few slides, but there's no need for a write-ahead log anymore because now, yes, your disk was persistent before, but now you can have transactional writes that are also fail-safe. And the read path is the exact same. You just query the storage engine, and you get your response from this engine. Now, I want to mention that we piggybacked on a pluggable storage engine API that was already brewing in Cassandra. So the persistent memory storage engine is here, and it can coexist with a disk storage engine, which is the default, or any other storage engine that might come about. So now, if we drill down into the Cassandra persistent memory storage engine, it uses open source components like the low-level persistent library. This is an open source library developed by Intel, and as well as PMDK. It uses this for transaction support and to provision the memory. The main data structure in this storage engine was an adaptive radix tree. We developed this from a paper, and we implemented this. It is single-threaded, so we've organized them in shards with queues at the top. It makes it simpler, and it scales very well. Like I described in the previous slide, it's a pluggable engine. So some of you might be asking, well, persistent memory, yes, it has all this capacity, but it's, at least today, it doesn't rival the capacity of your NVMEs or your spinning drives. So this design takes that into account. That's why it's pluggable. So you can have one table, your hot data on the persistent memory storage engine. You can have other tables on another storage engine. So we saw some pretty good improvement in performance on reads and writes, mostly from the simplification of the design. I've also included a link to this to the project. It is not currently upstreamed, but it's in the process. The storage, the pluggable engine API itself is still being worked on. So, excuse me. Another option that we could have taken. So all of this was a significant effort in the sense that there's a lot of code change here. It's a lot of re-engineering. But really, the only thing that we changed is in the persistent memory storage engine. The rest of the front end and everything else remains the same, unchanged. So another approach you could have taken was just leave everything exactly the same. Don't change anything, but use the storage over app direct mode that I described in a few slides before, where you have you point your Cassandra data store to a file on a persistent memory file system using actual persistent memory, and boom, you get not as much performance gain as this, but it's pretty modest. It's pretty good too. So I say that to just let you know that there are different ways, depending on the amount of engineering effort you're willing to put into it. There are ways that you could use persistent memory with no code changes, and if you want to extract more value, you could make some more changes or re-architect it a little bit. So on this slide, I'm going to talk about some things to consider when using persistent memory for persistent use. First thing is data integrity. I think we already touched on that a little bit. But just like Memcache D, on a controlled shutdown, if you want data integrity in the face of on a controlled shutdown, you need to make sure you flush the caches, right? Again, it's cache coherent, so you don't want, whatever is left in your CPU caches, if the system goes down, it's lost, right? So if you want your data to be durable, you need to make sure that you flush. And the next level, this is a stronger data integrity policy where on an uncontrolled shutdown, like a power failure or a crash, you could still have data integrity in that scenario. And how you achieve this is through transactions. And PMDK is a library, has libraries that provide transaction support. So really what a transaction is that if you can group a whole bunch of writes, and you can say, and you have the guarantee that they will all either execute or none of them execute. So if you crashed in the middle of that combined write, it would roll back for you. So again, that's data integrity in the face of an uncontrolled shutdown. So these are things that you might want to think about depending on how strict your data integrity policy is or how you want it to be for whatever you're designing. The next thing is concurrency. Now, if you want, again, we're talking about things to consider using persistent use of persistent memory. If you want concurrency and data integrity, you might want to think about this. So first of all, most lock-free algorithms use compare and swap, the compare and swap instruction. And if you want concurrency and data integrity, there needs to be a flush in there somewhere. But now compare and swap plus flush is not atomic. So using those same lock-free algorithms don't really transfer well to persistent memory because what you can do and what we actually did, we initially started off with a persistent version of the concurrent skipless map, and there are compare and swaps all over the place. But because we couldn't do that, because we wanted transactional behavior, we had to replace those with locks. Now you have locks everywhere. And there are performance implications of those. That's one of the reasons why when we re-implemented the storage engine with the R tree, we decided rather than trying to create some concurrent R tree, we just went the sharded approach. So we still have locks, but at the queue level, but everything down here is single-threaded. It makes things much simpler. And we got really good performance. So that's something to think about, concurrency. And then fragmentation. Fragmentation is a problem that exists today, but it's made worse by longer-lived heaps, or memory pools, if you will. So imagine this, your persistent data store that's supposed to live forever and ever. You will eventually run into fragmentation, and which you would have done, which we're probably all suffering right now in volatile use case, but because the processes don't usually live long enough for the problem to be that severe, we usually either shut down or the process exits. But if you have, if you have a persistent data pool, it's significant, and you need to think about this. So there are solutions available. Actually, I think the biggest solution is either do some kind of garbage collection or defragmentation or compaction. Another mitigation is you could manage memory in slabs, like we saw, the HBase bucket cache and Memcache D. Those were done specifically because of fragmentation. So you could do that too. That mitigates the problem, but it doesn't completely eliminate it. Also, if you're, from the application point of view, if you're aware of your allocation patterns, you could reuse memory. That will help with fragmentation as well. So these are some of the things that we, through our experience, again, this is not a comprehensive list, but from our experience, trying to apply persistent memory in multiple areas, these are some of the things that we think that you should also think about. So in summary, persistent memory is available, and it is valuable. It's in use today in multiple open source projects. Some of them are upstreamed in the trunk. Some of them are not. We've also learned that there are multiple ways to extract value from persistent memory. They range from no code change to data structure redesign. Also, there are libraries available to help with your persistent memory needs. I talked about the PMDK suite of libraries. That's open source. Also, the low-level persistence library for Java, that's, as the name suggests, a low-level persistence library for Java, which I helped to implement. And these are all ongoing projects that you could contribute to. There are links in the next slide. And if you don't want to use any of these libraries, you could just memory map a file and start doing loads and stores like you normally would. So that's all I got. Questions?
So you mentioned that the persistent memory is faster than NVMe. Is that also latency or bandwidth?
Definitely latency. I imagine bandwidth as well. I don't have the numbers on the top of my head.
Latency.
Well, I mean, definitely latency, yes, is in the nanoseconds. Interesting. Thanks for that. Any other question? Hi.
Slide 11, can you go to that real quick?
Slide 11.
Maybe it's 12.
One before?
Yeah, I'm looking at the engine, the actual engine itself. That's the controller for the Cassandra. What's the implementation of that? Does that have PGA or?
The engine that is, I'm sorry, the engine that is a controller for Cassandra? So you're talking about the, okay, let me go to the Cassandra slides. This guy?
Yeah.
Oh no, this is all software. And I mean, it uses persistent memory devices. There's no FPGA involved here. How is that implemented? This is the internal implementation of the engine.
You're calling it a storage engine. It's a software storage.
Mm-hmm.
You could use a smart SSD from Samsung, which has FPGA, something like that, to speed that up.
Yeah.
I believe you had a question.
Yes, question I had, the atomicity and durability of AppDirect PNAP. It's a very tricky problem.
It is a tricky problem.
And the problem is, it's easy to have a solution that's really inefficient. But do you guys have any thoughts on how to make the programming easier? And how do I take a very complex database or application product and instrument it to use PNAP? Because what we have seen so far requires a huge amount of re-engineering. It's not simple. And as a database person, for me, durability it's essential. The solution doesn't provide it, doesn't work. But logging every store and being able to undo any operation, it requires additional instructions that can, by the time you've done that, you could lose all the benefits of the PNAP latency reduction. If you double the instruction count, it doesn't help to have fast memory access.
Yeah, you're right. Transactional operations are definitely more costly than just regular writes. But it's still faster than going to a disk. And the first part of your question was, do you have ways to make this kind of programming easier?
Are you working on any libraries, anything to provide any SDKs for developers to use?
Well, yes. So the persistent memory development kit, again, is a suite of libraries ranging from, well, I'm not going to describe there's some low-level libraries that give you transaction support to higher-level libraries. The LLPL library that I talked about, one of the things that we do is we provide you with, you have the option to use a transactional heap or just a durable heap or just a regular heap with no data. So those are different levels of data integrity. So in a transactional heap, you don't have to do anything. Any writes to that is always transactional and fail-safe, and will roll back on any power loss. So in that case, it's simpler to use in that you cannot make a mistake and lose your data or corrupt your heap, right? So if you don't need such a strong integrity policy, if you just like the close to open consistency on like in Memcache D, if you know that, all right, I'm just if I ever crash, I'll throw everything away. But if I want to bring down my machine for, like, say, updates or whatever, so on a controlled shutdown, then all I need is just durability. Then we also have APIs that automatically flush for you, so you don't have to remember to flush. So when LLPL, low-level persistence library. Yes, it's a library for Java. Essentially, what it does is it gives you memory blocks. It allows you to provision memory. It gives you memory blocks as the smallest unit of persistent memory that you can deal with, and then transaction support. PMDK itself, I think there's a library called libpmmobj. This is, LLPL uses this library, and they have C++ bindings for that. So you can use libpmmobj itself, or the C++ binding, which are slightly easier to use. But it depends how low level you want to go. Any other questions?
What you've shown is basic persistent memory used in storage. There's very little data on how it's used as memory, particularly in memory computing. For instance, if you were to use NVDIM with a crosspoint, then you get into some pretty good ways of using persistent memory with the FPGA on the DIM to do some of the calculations, create a little bit of processing memory. Can you elaborate anything at all on that?
I cannot, because I have not done that work yet. But so all of this is all sort of new. And again, this presentation is really based on our experiences, my experiences. But that is very interesting. We have thought about persistent memory and some other kind of accelerators like FPGAs and stuff like that. But I don't have any data or any work that I have done to present today. Maybe next year.
Can you go to the last slide with the URLs?
Yes. And yeah, the slides will be available, all the links, or you can just take a picture of it right now. Any other questions? No questions? Okay, thank you very much.